Hello everyone, my name is Jerry and welcome to this session where we will be discussing various design patterns involving transactions when they are used in a microservices environment. Let me introduce myself. I'm the Director of Engineering at Appween, and at Appween I'm responsible for architecting and designing all products, including research on emerging technologies, microservices, APIs, and cloud. Over the last 5 years, my team and I have built various end-to-end solutions following the microservices architecture. Now let's get started. Here's a quick overview of what we will be covering today. We have a very simple agenda for the session, as you can see. We will go over transactions and what they are, just so that everyone can follow the session. After that, we will look at microservices, a quick primer on that, followed by the main topic of the session, which is the design patterns involving transactions. Let's talk about transactions. With the next set of slides, I will try my best to explain what they are, why we need them, and what problems it solves. Transactions are best explained with an example, and for that, let's consider a completely fictitious online fashion store, Adam and Eve Fashions. We are particularly interested in their order management system. This order management system has an application layer that exposes a set of APIs and a database layer that holds the business data. The order management system manages the online shopping cart of the user, the inventory, and all orders that gets placed. We are interested in one particular API of the order management system, which is the buy API, as shown here. The buy API helps the user to place an order. When an order gets placed, the system checks the inventory and makes sure that sufficient stock is available at hand. Once that is done, it waits for the payment confirmation, and once the payment is confirmed, the order is placed. Let's take a look under the hood to understand this process a bit more in detail. Here we are placing an order for a pair of shoes. In the inventory, we have 10 pairs of shoes available. The system receives the order request. We check and reduce the inventory and wait for the payment. Once the payment gateway or the bank acknowledges, as the order is then marked as confirmed, post which the cart is reset to zero. So when we reduce the inventory based on an incoming order, what's the confidence with which we can reduce it? What if some other order that came in at the same time is also reducing the inventory? Similarly, let's take a look at a failure scenario. We receive the order request, inventory gets updated, and now we are waiting for the payment status from the payment gateway or the bank. But now the payment gets marked as failed for whatever reason. In this case, we have to revert the changes that we did on the inventory. The cart obviously won't get reset as the order was not successfully placed. While reverting the changes, we have to ask the same set of questions. What's the confidence with which we can revert the changes that we did? What if some other order that came in at the same time is reducing the inventory while we were reverting the changes? This is where transactions help us. All the changes to the inventory, order, and cart are bundled as a single transaction by the application. We start a transaction, do the operations that we have to do on the data. Depending on the outcome of these transactions, we either end the transaction and commit or abort the transaction and do a rollback. It's essentially an all or nothing approach towards making changes to the data. Transactions are essentially a capability of the database. For a database to claim that it can do transactions, it has to guarantee validity even in the event of errors, power failures, etc. These set of properties or capabilities for such a database are atomicity, consistency, isolation, and durability. which are commonly known as the asset properties of a database. Transactions are often composed of multiple statements. Atomicity guarantees that each transaction is created as a single unit, which either succeeds completely or fails completely. If any of the statements of a transaction fails to complete, the entire transaction fails and the database is left unchanged. Consistency ensures that a transaction can only bring the database from one valid state to another. Transactions are often executed concurrently, that is, multiple transactions reading and writing to a table at the same time. Isolation ensures that concurrent execution of transactions leaves the database in the same state that would have been obtained if the transactions were executed sequentially. And finally, durability guarantees that once a transaction has been committed, it will remain committed even in the case of a system failure. Example, a power outage or crash. This usually means that the completed transactions are returned to the disk. So we can redefine transactions in the context of a database as a sequence of operations that satisfies the asset properties. And that's a quick overview of transactions. Now let's take a look at what MongoDB offers in terms of transactions. MongoDB transactions can be performed across multiple operations, multiple documents, multiple collections. These operations, documents, and collections can span multiple databases and can even be performed across multiple charts. The transaction capability of MongoDB do, however, come with certain limitations, where you cannot write to capped collection or you cannot read or write to some protected collection in the config admin, etc. I have provided the link below for you guys to read through what's supported, what's not supported, and things to factor in while going into production, amongst other things. Now I'm going to cover microservices in the context of what's needed for this session. This would give you guys an idea of what microservices are if you are not already familiar with it. As a disclaimer, this is not the only definition or the definite definition of a microservice. Just keep in mind that technology is just part of the entire microservices approach. To understand microservices, I'm going to compare it with a monolith. This comparison to a monolith or the monolithic architecture is a very cliched approach of explaining microservices, but it's the easiest way to understand what microservices are if you are not already familiar with it. If we take the example of a fictitious fashion store, the Adam and Eve fashions, there are all these components that make it possible for the entire store to be operational and usable for the consumers. Here, I have listed a few in the context of handling an order. Sorry, going back, trying this slide again from the beginning. If we take the example of a fictitious fashion store, the Adam and Eve fashions, there are all these components that make it possible for the entire store to be operational and usable for the consumers. Here, I have listed a few in the context of handling an order. In the traditional monolithic way of software development, or in a non-microservices world, all these components could be built as a single system with sub-modules handling or responsible for each component. Being a single system, we are also able to have a proper transaction setup between order, billing, and inventory. Now, the site is up and running. It's gradually gaining traffic. Orders are being placed and your revenues are going up. Everybody's happy at this point. Owing to the popularity of Adam and Eve fashions, you get the exclusive online deal of the next hottest apparel. This drives in a lot of traffic. As orders go up, you start to notice that your system is struggling to keep up with the increasing demand. You narrow it down to the slow response from the payment gateway, which is taking a lot of time to respond to each payment request. Your system is now straining to keep up with orders. The backlog of payment confirmation has now started to affect order, which is now unable to handle more order requests, which in turn is now affecting the overall user experience of your website. The system is now really struggling to keep up with all the new traffic it is getting. One way to solve this problem is to scale. The entire system can be scaled horizontally. This relieves the pressure on the modules and you are able to handle the traffic. But there is only so much you can solve by throwing money at it. Eventually, even this becomes inefficient to handle more orders. Let's take another scenario. You want to upgrade order module, or there's a bug in the billing system that causes a memory leak, and the temporary fix for that is that you have in place is to restart the system at midnight every day. Since the whole system is a single moving unit, any change would require you to bring down the whole system and then up again. Even worse, for some unknown reason, the database crashes and your application has no access to it for some time. The entire system is now inaccessible and out of action. Now let's take a look at Adam and Eve fashions as a set of microservices. Each module that we see here is an independent service that has its own database and is independently deployed. Each component talks to the other via clearly defined APIs. Like in the previous case, billing system is now under stress due to the slow response from the payment gateway. In this case, you can scale billing service alone to evenly distribute the load. All the other services continue to operate and are agnostic to the fact that the billing system has been scaled. And if the billing system needs to undergo emergency update, we can always scale the billing system, upgrade each running instance, and gradually move to the latest version. This potentially helps us to have zero downtime upgrades. So to quickly summarize microservices makes the application modular and easier to understand, develop, test, and deploy, thereby making it more resilient. It also enables distributed development, where small autonomous teams can now develop, deploy, and scale their respective services independently. You can read more about microservices from the link I have provided. Now that we are all on the same page with respect to transactions and microservices, let's move on and ask some questions. How will you do transactions in a microservices environment? What if your transactions span multiple microservices? Taking the example at hand, how can order, inventory, and billing take part in a shared transaction? Just because you decided to adopt microservices doesn't mean that now you have to worry about distributed transactions. Through the rest of the session, I will try and attempt to answer all these questions and more for you guys. Before we get into further discussions, it is important to discuss how transactions differ in SQL and in a NoSQL environment. Though both SQL and NoSQL takes identical approach towards transactions, the fundamental way in which both stores and retrieves data makes a big impact on how soon you have to deal with transactions. In SQL, because we have to normalize the data, the business data has to be split across multiple tables. The transactions are now schema-centric, which might force you to have transactions at a much earlier stage in the application development process. With a NoSQL database like MongoDB and its schema-free approach, business data need not be split across multiple collections unless it is done deliberately during design time. This makes transactions schema agnostic. Wearing sales or business hat, I would say this means you are better equipped to deal with requirements in a fast paced, chaotic world of evolving business ideas. Why? Because now you are no longer locked into a schema you thought was a great idea 2 years back. This session makes an assumption for the rest of the slides. The transactions and microservices we are going to discuss uses a NoSQL database like MongoDB. Let's now talk about the various design patterns that you could come across when transactions are used in a microservices environment. We move from the most simplest approach to the most complicated pattern. The complexity could be in terms of design, implementation, or both. Let's start. The first one is the novice pattern. It's the simplest approach for implementing transactions. Transactions are limited to a single microservice and happens with documents in a single collection. The relative complexity of this approach is very less, and so is the implementation. If I have to take an example for this, it would be a simple account transfer between two parties, say Jane transferring $10 to John. This approach, though simple, is not widely used. The main factor being that with proper data and business design, you're more likely to use one of the patterns that we are going to discuss. The next approach would be the beginner pattern. Transactions are still limited to a single microservice, but now they involve multiple collections, and these collections are on the same database. As compared to the novice pattern, this has a slightly higher design and implementation complexity, and you're more likely to use this pattern than the previous one or the ones that we would be discussing. The complexity here can be attributed to the business knowledge that is required to design and execute this. If we take the example of our Adam and Eve fashion store, the inventory management service could possibly use this mode of a transaction design. The inventory service is responsible for managing stock intake, the live inventory, and damaged goods inventory. Any stock movement from intake to live or moving inventory from live to damage would require you to perform your transaction that span multiple collections. Next up is the apprentice pattern. Transactions now start to span across multiple services, which essentially means that it now involves multiple collections, but it is still on the same database. In this approach, if a transaction has to span multiple services, one of the service takes control of the transaction and uses the documents from the other services collection during the transaction phase. This is now a complex design as you have to introduce a soft coupling between these independent microservices. There should be good reasons for you to use this approach, say like performance. And if you have control over these services, you should value simplicity of design over complicated API development and maintenance. Like in the case of Adam and Eve fashions, once the order is confirmed, the inventory is updated, and all this happens as one transaction. We are now slowly moving to, to more complicated patterns. Next up, we have the insane patterns. Compared to the first three patterns, the following would require proper design, documentation, and must be backed by a good engineering team. Failing to have one of these could result in a system that over time might be difficult to maintain. We can classify the insane patterns into two based on how the database have been set up. Mode 1 is where we deal with multiple services, multiple databases, but they all essentially run on the same database instance. Mode 2 is where the database instances are different or you can no longer guarantee the database instances to be the same. In the mode 1 approach of insane patterns, you can still approach the problem and solve it like an apprentice pattern. But since these services would be handled by different teams that are separated in some form or fashion, you need to ask some questions around what you and your team stand to gain or lose if this approach is adopted. And more importantly, what you would have to give up to adopt this. This works clearly well when there is already some form of communication set between the teams working on this, and whether or not the design for this approach has been documented. Let's now take a look at mode 2. If the situation does not favor a mode 1 approach, then it quite naturally leads to a mode 2 approach. We end up in a mode 2 situation with the earlier case, or if the database instances used by services are different and the service cannot participate in transactions using a shared session. With that, we are now going to deal with truly distributed transactions. Mode 2 is nothing but pure distributed transactions. The question here then is, how do we keep the database operations atomic? There are two ways in which we can approach distributed transactions: a synchronous or two-phase commit, or asynchronous or eventual consistency. Let's take a look at distributed transactions. The synchronous mode or two-phase commit is widely used in database systems. As it says in its name, two-phase commit has two phases, a prepare phase and a commit phase. In the prepare phase, all microservices will be asked to prepare for some data change that could be done atomically. Once all the microservices have acknowledged the prepare request, the commit phase will ask all the microservices to make the actual changes. One important participant is the transaction coordinator or the coordinator, which maintains the lifecycle of the transaction. Let's take a look at how this works. The incoming request to place an order is handled by the transaction coordinator. The coordinator service then starts a global transaction with all the context information. It then proceeds to call other services with a prepare request with the context of the incoming request. In this case, prepare on order would create a new order, billing will start checking for available funds, and inventory service checks if there is enough stock available to complete the order. Once all the checks have been completed and is successful, the prepare request returns a success. The coordinator will now issue a commit request to process the changes into the DB. And once the change has been committed, the coordinator ends the transaction and returns the success response. Now let's take a look at how an error case will play out in two-phase commit. We are at the prepare step and billing returns an error, say due to lack of funds. The coordinator now sends an abort request to all the services except billing to discard the changes that were made during the prepare phase. It then ends the transaction and sends the error response. Two-phase commit or synchronous mode has its advantages and disadvantages. Two-phase commit is a strong consistency protocol. The prepare and commit phase guarantees that the transaction is atomic, which means two-phase allows read-write isolation. This means that the changes on a field are not visible until the coordinator commits the changes. It is also synchronous. The client would be notified of a success or failure. While two-phase commit has solved the problem, it is not really a recommended approach for many microservices-based solutions. Well, because two-phase commit is synchronous or blocking. Since it is synchronous, it is quite slow considering the time it takes to complete the operation. These operations are dependent on the transaction coordinator, which can really slow down the system during high load. In the example that we looked at, the request response cycle in this case will have to wait for the entire process to finish before a success or an error response can be sent. The other main drawback is the explicit requirement for having to acquire and keep logs. It is possible where this approach could potentially lead to a deadlock where two transactions mutually lock each other out. Also, transactions are meant to be faster, and holding on to logs will become a performance bottleneck. The second method of approaching distributed transactions is to make it asynchronous. This is called the asynchronous mode or eventual consistency and compensation, or the saga pattern. Each business transaction spans multiple services as a saga. A saga is a sequence of local transactions. Each local transaction updates the database and publishes a message or event to trigger the next local transaction. If a local transaction fails because it violated some business rule, then the saga executes a series of compensating transactions that undo the changes that were made by the preceding local transaction. As you can see, this is quite complex. This requires a level of design where compensating transactions needs to be designed and built that explicitly undo changes which were made earlier. There are two ways of implementing sagas: choreography and orchestration. In the choreography-based saga approach, each local transaction publishes domain events that trigger local transactions in other services. One of the critical and most crucial services receives the request and then executes the most critical step in the system. In this case, it is the creation of order and getting the billing status. Once that is done, the user gets a response. It would be then up to order or billing to call or propagate or trigger operations on inventory. In the case of an error, the compensating transactions are triggered upstream and the orders eventually get updated to the correct status. Let's take a look at orchestration-based saga. The orchestration-based saga requires an orchestrator to tell the participants what local transactions to execute. This could be an independent service as shown, or it could be part of one of the critical services. Once the request is received, just like in the choreography-based saga approach, a critical component executes and based on the outcome, a response is sent. In this case, a partial success response has been sent back to the client, which is denoted by the HTTP 202 accepted status code. All other operations are orchestrated from this service, eventually resulting in the order being updated. If there is an error in one of the services, the orchestrator takes care of calling the rollback or compensating transactions till the system returns to ideal state. The eventual consistency mode of distributed transactions is, in a sense, not a true distributed transaction. It is a sequence of microtransactions that is either choreographed or orchestrated to achieve the desired business state. It enables applications to maintain, starting the slide from the beginning. The eventual consistency mode of distributed transaction is, in a sense, not a truly distributed transaction. It's a sequence of microtransactions that is either choreographed or orchestrated to achieve the desired business state. It enables an application to maintain data consistency across multiple services, and each of these services does a local transaction. The asynchronous nature of this approach makes the system highly scalable under heavy load. The main disadvantage in terms of business operation is that this doesn't offer any read write isolation, which means in the above example, the client could see the order was created, but in the next second, the order is removed due to a compensating transaction. It also gets complicated to design, develop, and debug when there is a failure. I cannot stress sufficiently enough the importance of logging in this context. Another drawback is that the programming model is more complex. For example, a developer must design compensating transactions that explicitly undo changes made earlier in a saga, which would also mean that proper documentation about the design and approach has been created and maintained. This becomes vital over time when the system needs maintenance. With that, we have come to the end of this session. Here's a quick recap of what we looked at in terms of transaction patterns. The design decisions are driven by whether the database instance is separate for each service or shared. And within that, we can have varying levels of complexity. One important takeaway for you guys is that you should find a pattern that not just justifies the technical need, but also addresses the business as well. And don't be afraid to break the conventions to achieve your goals. Before I end, here are a few links to get you started. Thank you.